Hello everyone, welcome to my channel. In this lecture we will discuss about the water gas shift reaction in the DWSIM software. So this is a problem statement. This is about the water gas shift reaction. The new application of hydrogen as a raw material for automobile power sources required the anode in that gas which have about less than 20 ppm carbon monoxide. Otherwise the anode is poison and the cell efficiency abruptly drops. So hence, if hydrogen is produced from the hydrocarbon alcohol, requirement purification is required in order to reduce the CO2 level to cell requirement. The most technologically feasible purification trains consist of water gas shift reaction. This is a water gas shift reaction, and it is used in industry for about 40 years for the production of hydrogen and gaseous hydrocarbon. Add carbon dioxide. So the role of water gas shift reaction is to increase the hydrogen yield and decrease the concentration of carbon monoxide gas, because these carbon monoxide poisons some of the catalysts which are using in various reactions. So this is the water gas shift reaction. We will use this water gas shift reaction in the DWSIM software using the equilibrium reactor. So first of all, open the DWSIM software, click on the create new. Now click next to continue, and this water gas shift reaction consists of the carbon monoxide and steam. Carbon monoxide react with steam in the form of water, and it produces the carbon dioxide and hydrogen gas. Carbon monoxide, steam, carbon dioxide and hydrogen. So carbon monoxide, steam, carbon dioxide and hydrogen. Okay, now click on next, and here you can use the property. So in this problem, in this question they have used, so we can use the Finn-Robinson equation of state or some other thermodynamic package. So I am using the Finn-Robinson equation of state. Okay, click on add. It is added. Click on next. Select system of unit. I am using the C5. Okay, click on next and click on finish. Now select the stream. So this is the one stream, and this is the steam. This is methane, and this is this water. Okay, steam. This is carbon monoxide, CO, and this is steam. Okay, now the flow rate, temperature, pressure of these are given. So the steam information is given to us. So the steam is at 102 bar pressure and 100 kilomole per hour, and it is a pure steam. So 100 kilomole per hour, 100 kilomole per hour, 2 bar pressure, and 100 degrees centigrade. And it is a pure steam. So steam, it is pure steam, so it is 1 0 0. Okay, you can accept. Okay, it is a pure steam. Water mole fraction is 1. Go to the carbon monoxide, and here it is also a pure carbon monoxide. So here we will use the carbon monoxide is pure. Okay, click on accept changes. Carbon monoxide, pure carbon monoxide. Okay, now this is okay. Now go to the reactor. Now go to select the go to setting and add reaction. So we will add the reaction. So click on setting and here go to the reaction. Click on this add button and this is equilibrium reaction slope. So click on equilibrium reaction and name it reaction number, suppose reaction number 3. So in this reaction the carbon monoxide, 1 mole carbon monoxide react with 1 mole steam, it produces 1 mole carbon dioxide and 1 mole hydrogen. Base component is the carbon monoxide. Suppose the carbon monoxide is the base component and this is 1 1 1. Stoichiometry is okay. Click on balance and here the base is either pugosity or can be concentration, so I am using the partial pressure and the unit I am using the bar, and the phase is it is in wafer phase. Okay, the minimum temperature is 0, maximum this is okay. Temperature approach calculate from Gibbs free energy of reaction. So the equilibrium constant will be calculated from Gibbs free energy. If we have know about the equilibrium constants, for example, if equilibrium constant is 0.44, you can put in this place the ln KEQ, or you can obtain from the ln function. This, if you have information, you can be obtained from the Gibbs free energy. So we will obtain from Gibbs free energy because we have no information about equilibrium constant. So Gibbs free energy calculation will obtained. Will calculate the equilibrium constant of the equilibrium reaction. So click on OK and now close this one. Go to the reactor here and go to the equilibrium reactor. Go to the equilibrium reactor. Okay, close this one. This is energy stream. And this is okay. This is the product, top product, this is the bottom liquid, this is the reactor, equilibrium reactor, this is the energy. Okay, now add. So now add, this is, we cannot add this stream. So first of all we will remove this one and we will combine these two streams. So we will delete this one. Suppose I am deleting this one. Okay, delete this one, delete this one. Okay, delete this one and this one. Now mix, we should mix this and then we will add to the reactor. So we will go to the mixer, drag and drop mixer. Okay, stream number 5, mixer outlet, mixer out, mixer out. Okay, now we will go to the reactor and equilibrium reactor, drag and drop the equilibrium reactor. This is equilibrium reactor. Reactor. This is the energy. So energy. This is mixer. This is equilibrium reactor. Okay. This is the top product. This is the bottom. Reaction defined. So now click on the solve button. So it is some error, unable to calculate compressibility factor at the given condition. So we cannot calculate the compressibility factor 100, and this is 25 degrees C. So we will this is 25 and this is 100 and this is 25. So we will, suppose I am changing this one to 50 degrees centigrade and this one to 2 bar pressure. Again it shows some error, we cannot calculate the compressibility factor. So the carbon monoxide, suppose it is again 25 degrees, okay, 25 degree and 1 bar pressure is okay. Now we will change the package. So go to the thermodynamic and select the Chow Cedar, add it and remove the pin Robinson. So we will check that whether it work or not. Now click on solve button. So it is taking some time. It will take some time. So we can, suppose I am changing this one to 45 degrees centigrade. This is to 2 bar pressure and now solve it. So it shows some error. Again 25 degrees, 1 bar. One or more stream in the output are not calculated, okay. 1 bar. Okay. Click on solve button. So it is taking some time. So there is some error. We will use select another. Suppose I am adding some other NRTL. Suppose NRTL. Add the NRTL. Remove this one and check whether it work or not. Again assume X is enthalpy. It also shows some error. So go to setting and add some other package like unific method. Add this one, remove the previous one, this one, click on solve. So it shows some error. Now I'm changing the temperature. Suppose whether it works or not. Error. Okay, now I'm changing it to some other fluid package like the SRK. Select the SRK, click on add, delete the previous one and solve. Unable to calculate compressibility vector at a given condition. So these conditions are, I think, okay. The molar flow rate here you can see it is 100 kilomole per hour and this is 128. So suppose I am changing it to 50 kilomole per hour. 50 kilomole per hour, and suppose the pressure is 2 bar, temperature is 15 degree. it is 80 degree. So show some error. Go to this reactor. This is the diabetic, so we will change it to the isothermal, and now solid. So flow sheet is being calculated, please wait. So for isothermal reaction we will see what will be the composition of the top product. So it is taking some time. So it is calculated. Now it is calculated. So at these condition, when the carbon monoxide temperature is 80 and 2 bar pressure, and when the molar flow rate of carbon monoxide is this one, so this amount of energy for the this will be the isothermal reactor energy. So here you can see this is the gives free energy. The heat load of the reaction is this of the reactor is this one. This is the heat load of the reactor 136.61 kilowatt, and this is for the isothermal condition. And now go to the product, and here you can see, click on the top product and click on the composition. So here you will see this amount of carbon monoxide is present, and this is the hydrogen, quite large amount of hydrogen and carbon dioxide is present. Water is 11%, carbon dioxide and hydrogen is 44%, and this is very small percent of carbon monoxide. So we can decrease further, the concentration, because it can poison the catalyst. So this is the top product, and the molar flow rate of the top product, you can see the molar flow rate of the top product is 113.619 kilomole per hour. The mass flow rate is 2546 kilogram per hour. So it is okay. Now go to the bottom, and here go to the compound, and here in the bottom there is very small amount, there is no very small amount, large amount of water is present in the bottom. So in the bottom large amount of water is present. So okay, now you can change. So this work for the SRK equation. Now I'm changing it to, for example, I'm changing it to 25 degrees centigrade and 2 bar pressure. So now this is the duty of the reactor, and the top product here, now the top product composition is this one. It is 44 and this is 10%. It is not decreased. So you can change 25 degree. Here there is 25 degree and 2 bar pressure. Now I'm changing it to 1 bar pressure. 1 bar pressure, and it shows some error. It is not working at 1 bar pressure. I think it is not working at 1 bar pressure. So I'm changing the molar flow rate, suppose to 70 kilomole per hour. Again it show, please wait, it is calculating, so it will take some time to calculate this flow sheet, whether it work or not. We will check it. So it is time taking process. So it is calculated. 156 is this is 156. Okay, this is the 156, and here the energy is 156 of the reactor, and the top, go to the top, and now you can see 43. It is slightly decreased. It is decreased. So it depends a lot. It also depends on this temperature, pressure. So suppose now I'm changing it to 60 degree and 2 bar pressure. So this is, now go to the top, and here it is 45. So when we increase this temperature of this and we increase the pressure, so we will get large amount of hydrogen and carbon dioxide. So the reaction will be go to the forward direction when we increase the temperature and pressure. So this is all about the water gas shift reaction, that how can we minimize the concentration of carbon monoxide. Here you can see the carbon monoxide is zero, and here the water is large amount of water, carbon monoxide is 0. Okay, so this is for the isothermal. You can also draw the insert the property table like master property table. Click on this one, double click on it, and this is the C out, this is the mixer out, this is the top, bottom, this is carbon monoxide, the temperature, pressure, mass flow rate, molar flow rate. Select these all, and these are the, you can see this is the temperature, pressure of, this is of the bottom, temperature, pressure, mass flow rate, the top, temperature, pressure, the carbon monoxide, temperature, pressure, mass, and this is the mixer outlet, temperature, pressure, steam, temperature, pressure, mass, molar flow rate. So you can delete, I will delete this one. Okay, so this is for isothermal. You can check for the adiabatic, so check for the adiabatic, click on solve button. So it is show some error for the adiabatic, so we will choose the isothermal one. Okay, thank you very much for your attention. If you are new to the channel, please like and subscribe for upcoming videos. Thank you very much.